Welcome back. In this video, we're going to be talking about how to adjust the margin of error in the one sample Z interval for P. So specifically what I have boxed here. So we're going to do a little activity on Statplet. So if you go to statplet.com and go down to concepts, simulating confidence intervals. We'll go to categorical again. And let's make our true proportion. We'll do it something low. We'll do like 0.3. All right, so we got a 30-70 kind of situation here, 30% success, 70% failure. And let's make our confidence interval 95%, and we'll do samples of size. We'll start with 30. That's a good one to start with. And you might get a bunch of confidence intervals, and let's look at the width of that interval. Pretty wide, 95%. It's going to capture quite a lot. And maybe I do 100 samples, and maybe do 50. And you can see that they're all going to be the same width. Some will capture, some won't. And remember, about 95%, since our interval is set at 95%, we'll capture that. Now, if I keep that 95% and make my sample size smaller, so let's say I do a sample size of like 10, and let me do a bunch of samples. You notice that your interval got a lot wider here. Okay, with a much smaller sample size, you're going to have a lot more error, so the interval will be much wider. If I make my sample size like 100, the sample got even narrower. Larger sample, more precise, narrower interval. Sample size of 1,000, even more narrower, so it's going to be more precise, but it's still going to capture the same percent of the interval. So it's just going to be more precise, and that means it's going to have a narrower interval. Now, if I have a larger sample size, it's going to be a narrow interval. If I take my level and say I make that level, we'll say a 99%, probably helps if I make a normal sample size. We'll do 100. So there's 99%. Let me remind you what 95% looks like. 95 is a little bit narrower. And if I go down to, let's say 80, it's even narrower. I don't know if it'll let you go below 80, but I'll try 70. Yeah, so the lower your confidence level, the narrower it's going to be. And you might think that's not a bad thing, but you know you're not going to be as confident. So there's a trade-off. So the less confident you are, sure, you won't have as big of a margin of error, but you just won't be as likely to capture the true parameter. So if I look at those samples, if it's set at 70%, in the long run, I'm only going to capture about 70% of the true proportion that's in here, 70% of the time. So summarize that, where if you increase the confidence, or if you decrease the confidence level, it's going to reduce the margin of error. If you increase the sample size, it's also going to reduce the margin of error. So usually it's more preferred to increase the sample size because we want to try to be as confident as possible. So a higher sample size can offset a reduction in your confidence level. A bias isn't going to impact that margin of error. It might impact the sample statistic and the point estimate, but it's not going to impact your margin of error. So bias will never factor into that. So let's look at an example. In example one, we were 95% confident the interval from about zero point 0.2 to 0.26, remember that 20 to 26%, captures the true proportion of all cell phone users who admit to walking into something or someone while talking on their cell phone. In the previous video, we calculated that. This interval was based on a random sample of 738 cell phone users. And we have three questions. Explain what would happen to the width of the interval if the confidence level were changed to 99%. Part B, how would the width of the 95% confidence interval based on a sample of 1,500 compare to the original sample, which only had 738? And then part C, give an example of response bias that could affect the results of the survey. How does this affect the margin of error? Let's look at the first part. So explain what would happen to the width of the interval if we change it to 99%. Well, let's look at our formula. Let's kind of picture what this formula looks like. It's statistic plus or minus critical value times the standard error. Now, that Z star we get from the critical value. That's going to be based on our confidence level. So 99% is what they're asking us. Now, that 1.96 came from 95%. So that was our original one. But if we go to 99% and you calculate your Z star, it's going to be a larger number, 2.576. So the higher that critical value is related to the confidence level. That's the only thing that determines your critical value. So think about what happens when that number is bigger. You're multiplying by a bigger number. What does it do to your margin of error? Well, your margin of error is going to increase as a result. So you're going to have a wider interval as a result. A bigger margin of error is going to make that interval wider. How would the width of a 95% confidence interval based on the sample of 1500 compared to our original 95% confidence interval, assuming the sample proportion remained the same? So all else aside, keeping the same confidence level, what's going to happen if I use 1500 as opposed to 738? Well, let's think about the formula. So this is going to affect your standard error. So if I plug in 738, I don't know my sample proportion right now. I don't really care. But let's say I divide by the square root of 738. Now what's going to happen is if I increase that to 1500, I'm dividing by a larger number. So as a result, it's going to make my standard error smaller, which means my interval is going to be narrower. So take a look at this calculator operation here. So if I plugged in 23%, 77% for my p hat 1 minus p hat, and my 738 is my sample size, and I kept the same critical value. Notice I get a margin of error about 3%. Now, if I do that again with a sample size difference, so I'll keep everything else the same. So what was it, 1500? It will decrease my margin of error, which is going to be about 2.1%. So larger sample size will decrease the margin of error. And if I go back over here, if I keep the sample size the same, we'll verify the other part of that. So if I do 738 and I do 2.576 here, so we'll just say 2.58. You're going to see that I'm going to have a larger margin of error. So higher confidence level, larger margin of error, higher sample size, lower margin of error, narrower interval. Give an example of response bias that could affect the results of the survey. How does this affect the margin of error? Well, it's possible that not everyone would answer this question truthfully, maybe. So the sample proportion may underestimate the true proportion that admit to walking into things on the phone. That's just an example. You could have other things too. But does that affect the margin of error? No. It might affect the sample proportion, but it's not going to affect the spread. So that'll take care of that. Finally, this is kind of probably the trickiest part because it's going to involve some algebra. Sometimes we're going to have to estimate a sample size based off of what our margin of error should be and our confidence level should be. And here's some information about it. So how to figure out the sample size based off of maybe a previous situation is going to be a little tricky. So let's do a different example instead. And I'm going to do this with one way with before I solve it, just kind of playing around with the numbers so you can kind of see what's going on. So a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that will be required. One value of interest is the proportion P of customers who are satisfied with the company's customer service. The company president wants the estimate to be within 3 percentage points. So it's less than or equal to 3 or 0.03 at a 95% confidence level. So you already know it's going to be 1.96. And it says, what's the sample size needed? So let's kind of imagine what this is going to look like first. So before I get into more formal things, we want to think about this. It's that Z star. I'm just going to write this out for now. Square root p hat 1 minus p hat over n. And what I want it to be within 3 percentage points. So I don't want my sample size or my margin of error to be anything above 3%. So less than or equal to 0.03. Now in this question here, are we provided the sample proportion? I don't see a proportion anywhere. I do have this 1.96 for z since it's 95%, so I can call that 1.96, but I don't have my p hat. All right, so in this case here, what you want to do is you want to call your p hat 50% if you're not provided one to use. So we're going to make that 0.5. That's going to give you a conservative estimate. So we'll do zero point 0.5, 1 minus 0.5, so is also 0.5 over n less than or equal to 0.03. And that's what you want to solve. Now let's talk about what that looks like informally before I get into all the ins and outs of what that equation looks like. So let me look at this here. Let me go over here for a moment. So if I do 1.96, you can probably just pull out your calculator and try to play around with it and square root. And I'm going to go ahead and just do a fraction. So alpha y equals, and we'll do 0.5, 0.5, close it up. And I don't know n. So I don't know. We'll start with 500, see what happens. And we want to see, is that going to give me a number less than or equal to 3%? Well, it looks like it's too high, right? It's only 4.38%. So we're going to have to go higher than 500. So maybe the next logical choice would be 600, and that's still too small. So we can keep playing around with it. I'm going to try 900. We're getting there, but we still got to get under 3%. So this could take a while. So there's maybe 1100, and well, that's under 3%, but do I need to go as high as 1100? And you can see that could be very time consuming. So if you do want to use your calculator to solve that, you can do something like this. So you can go to your y equals, and you can do 1.96 square root, so second x squared, alpha y equals for the fraction, 0.5, 0.5, and you can go down here and just call it x. And what you can do is you can go into your table. Now you can scroll down to 1,000, but that's going to take you a while. You can see the higher I go, the smaller my margin of error becomes. Well, I don't want to do that, so I want to go into my second window and I want to set my table to ask. So instead of auto, make your independent ask, and then you can go into a second graph and you can start playing around with numbers. So let's do 1,000. Let's do 1,050. I think 1,100 was too small or too large. So let's do 1,060. And we're getting there, 1,070. And that's really close, but you can see 1,070 is just under. So can we do something like 1,069? And that's going to be just under. Let's try 1,068. And then 1,067. And you can see 1,067 is just a little bit above. So 1,068 is the very, very smallest number I can get away with being under 3%. Now that's a lot of trial and error. So I have a way that can solve it for you, but this is going to be a process and you have to remember how to do it. All right, so here it goes. First, you plug your 3% into the formula. Second, you identify your Z star, your P hat, your MOE. Remember, if you're not given a P hat, just use 50%. We're going to plug in our 1.96, our 50%, and our 0.03 into the formula. Now we're going to solve this. So watch the steps here. First thing you want to do is divide both sides by the 1.96. So we're going to bring that 1.96 over here and bring it down. Then we're going to square both sides. We're going to get rid of that square root. So remember, squaring that, we'll get rid of the square root, and that'll give you this fraction squared. Next thing I do is I solve for n. So what I'm going to do is I'm going to bring the n up here and bring this fraction down below the two proportions multiplied. So 0.05 times 0.05 divided by this fraction here. And let's put that in the calculator. So I would do, I'm going to do a fraction menu. So second y equals 0.5, 0.5. And then on the denominator, I'm going to do another fraction. So parentheses. Oops, let's do the parentheses out here. It's gonna be a little tricky entering it in if you're not careful. So we'll do 0.03 over 1.96. Close it up, hit that squared button. So that's how you would input it into your calculator. If you want to do it one step at a time, you can do the 0.03 and you can divide by 1.96, press enter. And then you can hit the x squared button. Make sure you do the previous answer. Now it's going to give you it in scientific notation. So just very carefully do 0.5 times 0.5 and then divide by, just scroll up. You don't have to retype it. Press enter and you'll get 1067.111. Now, in these problems, when we're solving, we don't want to round down. So we actually want to round up because 1067.11 is not going to be quite enough. So we're going to round to the nearest whole number, but always up. Even if it's closer to the one below it, always round up. So 1068 is going to be the smallest sample size in this problem. Well, we have a check your understanding. You're going to want to pause this video and try it on your own. So go ahead and pause it. Sleep Awareness Week begins in the spring with the release of the National Sleep Foundation's annual poll of U.S. sleep habits and ends with the beginning of daylight savings time, when most people lose an hour of sleep. In the foundation's random sample of 1029 U.S. adults, 48% reported they often or always got enough sleep during the past 7 nights. Describe 2 ways that the National Sleep Foundation could reduce the margin of error in its estimate of the proportion of all U.S. adults who would report they often or always got enough sleep during the past 7 nights. What are the drawbacks of these actions? And B, what's the minimum sample size required to have a margin of error at most 1% with a 99% confidence? Use the value of p hat from the original sample. So we're going to go over this in 3, 2, 1. So describe 2 ways the National Sleep Foundation could reduce the margin of error. Well, one way to reduce it is we're going to increase the sample size. Bigger sample size, lower margin of error. What's the drawback? It may be hard to get more people for the survey, so that's going to be a potential drawback. Another way to reduce the margin of error is to have a lower confidence level. Now, what's the drawback to that? You're not likely to capture the true proportions. So a lower confidence level will have a smaller margin of error, but might not be as likely to get the actual proportion. Now, here's the algebra. What's the minimum sample size required to have a margin of error at most 1% with 99% confidence? Use the value of p hat from the original sample in your calculations. So remember your formula is z star p hat 1 minus p hat over n in the square root less than or equal to a margin of error. In this case here, we're actually given a p hat, so 48%. And you want to solve that, use your calculator. That 0.01 came from the 1%. That's your margin of error. And why did we use 2.576? That's because of this level. So that's going to be determined by the confidence level. All right, see if you can solve that. I'll walk you through how I do it in the calculator. I usually just do it one step at a time. So I'll do 0.01 and I'll divide by 2.576. And then I hit the x square button. Then I do my proportions multiplied. So 0.48 times 1 minus 0.48, or you can do 0.52. And then I hit divided by, and then I scroll up and I press enter. And that's a large sample, 16562.89. So we're going to round that up to 16563. You can also do it in one operation in your calculator like this. So the smallest sample size would be 16,563. All right, that concludes our lesson. So there's kind of 5 steps to construct and interpret a confidence interval. Name the procedure, talk about the parameter and context. Remember, that's called the state part. The conditions are the plan, so the random 10% large counts. Calculations, use your stat menu, that's fine. Make sure you write those out. And your conclusion, we are blank percent confident the interval between this and this captures the true proportion of whatever your context is. And then if there's a follow-up question, make sure you answer that. Margin of error, higher confidence level, higher margin of error. Higher sample size, lower margin of error. Bias and sampling has no effect on the margin of error. And to solve for the sample size, you can use this formula here. It's the p hat 1 minus p hat over the fraction margin of error over the z star squared, and always round up. If you're not given a proportion to use, just use 50%, or if you're asked to use a conservative estimate. Thank you for watching.